In this presentation, we'll look at how quickly systems respond, and for that purpose, we'll introduce the notion of time constant. Now, for this analysis, we'll start by discussing the step response of a linear time invariant system. So we have an input x of t and an output y of t. We'll be examining the zero-state response of a causal system. So y of t is equal to the integral from 0 to t of x of t minus tau, h of tau, d tau. The input will be a step, so x of t will be 1 for t greater than 0 and 0 for t less than 0. Since x of t is 1 for t greater than 0, we find that the output to the step input is y of t equals the integral from 0 to t of h of tau d tau. Let's suppose that the impulse response of the system, h of t, looks like a pulse of amplitude a and duration cap t. This is shown in the figure here. In this case, the output, y of t, will look as follows. It will be a ramp starting at time 0 and ending at time cap t, and will go to a final value of a times cap t. After time cap t, it will be constant. So what we've done is we found the step response of a very simple system, one whose impulse response is a pulse of duration cap t. What we'd like to consider is how quickly the system responds and how this is related to the shape of the impulse response of the system. You will have noticed that the output reached its final value at time t equals cap t, and cap t was the duration of the impulse response. So we see there's a correlation between how long it takes the system to respond and the duration of the impulse response. We say that the duration, therefore, gives a characteristic time for the speed of the response. Now, the other thing I'd like you to note is that the rate of change of the output is constant during the time of the ramp from t equals 0 to t equals cap t. And this is because the rate of change of y is equal to h, and h is constant and equal to a during this time. Now let us consider how to find the time constant for a system whose impulse response does not have finite duration. So here is an example. H of t is 0 for t less than 0, and h of t is a e to the lambda t for t greater than 0, and lambda is less than 0. The impulse response is as shown in this figure. Note that the impulse response does not go to 0 until infinite time, and this is called an infinite impulse response system. I'd like you to also recall that dy dt is h of t, and so what that says is that y will change quickly at the beginning when h of t is large, but then as time gets larger, y will change more slowly since h of t is small. This is shown in the figure here. We see the impulse response on the left and the step response on the right. And we note that there's a fast rate of change in y of t at the beginning, but then a slow rate as time increases. The solution here is y of t equals minus a over lambda times the quantity 1 minus e to the lambda t u of t. Now, since lambda is negative, the negative a over lambda is a positive number. We found this solution by performing the convolution, and that can be easily done using the convolution table. Since h of t is of infinite duration, we know that the output y of t will not fully respond until infinite time. So how do we set a characteristic time for this system, since the duration is infinite? Before, when we dealt with h of t being a pulse, we saw that the time to fully respond was the duration of the pulse. But now we're dealing with an infinite impulse response system. So we cannot use the duration to try to characterize how quickly the system responds. You see, there are many infinite impulse response systems, and some respond faster than others, although all do not receive their full response until infinite time. So we need a practical way to sort amongst the infinite impulse response systems and classify which ones are faster and which ones are slower. We still need to define a characteristic time constant for these systems. I'll now clarify how we can solve this problem. I'll start by noting the maximum rate of response occurs at time t equals 0 plus, and that maximum rate of response is a, which is the coefficient in the impulse response, ae to the lambda t. This maximum rate of response is the initial slope of the response curve. So here is how we'll define a characteristic time for a system with an infinite impulse response. We'll find the maximum slope, which occurs at time t equals 0 plus, and we'll continue this line until we reach the final value of the system response, which would occur at time infinity. In this case, that final value is negative a over lambda. Where these two lines intersect, we'll define a particular time, which is labeled cap t, and this we will call the characteristic time. It's the time necessary to reach the final value if the rate of change was constant and equal to the initial and highest value of the rate of change. Since the slope is a and the final value is negative a over lambda, we can now find cap t, and cap t will be equal to negative 1 over lambda, and this value cap t is referred to as the system time constant. The time constant characterizes the speed of response of the system, and you'll note that it's related to the characteristic value of the system. Since the impulse response can be written in terms of the characteristic value, and the characteristic value is related to the time constant, we can write the impulse response in terms of the time constant, and that is shown here. H of t equals e to the minus t over cap t, u of t, where cap t is the time constant of the system. Recall that we can plot our characteristic value in the complex plane. We denote it by an x here, and in the case we're considering, lambda is negative. We saw that the time constant was negative 1 over the value of lambda. So when lambda is negative here, the time constant, of course, is positive. And the inverse relationship to this is lambda equals minus 1 over cap t, the time constant. So what these relationships are saying is that the speed of response of a system depends upon where the characteristic value is in the complex plane. To illustrate, let's consider two systems, System A and System B, and I'm showing the complex plane for each of these with the characteristic value marked by an x. The question I want you to consider is, which one of these systems has a smaller time constant. A smaller time constant corresponds to responding faster. So which one of these systems responds faster, System A or System B? And the answer is System B. And the reason why is because System B has a value of lambda that is more negative. With a more negative value of lambda, the time constant will be smaller because t equals -1 over lambda. A smaller time constant means faster response. After all, the time constant is characterizing how quickly the system reaches its final value, or how quickly it approaches it. Now let's consider a system with two characteristic modes. How fast will it respond? And how is this dependent upon the characteristic values? So the case we're looking at is h of t is c1 e to the lambda 1t plus c2 e to the lambda 2t times u of t. And both lambda 1 and lambda 2 are negative, with lambda 2 being more negative. We can plot the two characteristic values in the complex plane, as shown here. The impulse response will then look as follows. H of t will decay quickly at the beginning, and then will slowly decay. This is because h of t is the sum of the characteristic modes, and one value of lambda is much more negative than the other. So what is the step response of a system with this impulse response? Which mode will dictate how quickly the system will fully respond? Here you can see the step response for this system, and what you'll note is the slow mode dictates the time constant. The initial response of the system for very small time is dictated by the fast mode, but after the fast mode has fully participated, it is the slow mode which will dictate how quickly the response rises. Therefore, the effective slope that we need to consider is the slope associated with the slow mode, indicated here with the blue dashed line. We look at where this intersects with the final value to define our time constant. As a result, it is the slow mode that dictates the time constant. The slow mode is associated with characteristic value lambda 1, which is the characteristic value closest to the origin in the complex plane. In addition to the time constant, there is another way that we can specify how long it takes the system to respond, or how quickly it responds, and that is the rise time, which is given the symbol t sub r. The rise time is the time required for the output to rise from 10% of the final value to 90% of the final value, when the input is a unit step. We show the rise time in the figure here, the time to go from t sub 10 to t sub 90, the times corresponding to 10% and 90% of the final value. How is the rise time related to the time constant? Are they the same? We'll examine the single mode case, as the multiple mode case is difficult to do. In the single mode case, we have h of t equals e to the lambda t u of t, where lambda is negative. That's because the system is stable. Then, the time constant, cap t, is equal to -1 over lambda. In this case, the response to a unit step input is y of t equals -1 over lambda times the quantity 1 minus e to the lambda t u of t. Using this unit step response, we can then find how long it takes to get to 10% and 90% of the final value, and then compute the rise time. The final value of y of t is minus 1 over lambda. The time to reach 90% of this will be given by this equation. 0.9 times negative 1 over lambda equals negative 1 over lambda times 1 minus e to the lambda t90. This is just using the step response equation and plugging in for 90% of the final value. We can then find the time to reach 90%, and it is 1 over lambda times the natural log of 0.1. In a similar fashion, we can find the time to reach 10% of the final value, and that will be t sub 10 equals 1 over lambda, natural log of 0.9. Therefore, the rise time for a single mode system is given by t sub r equals t sub 90 minus t sub 10, or t sub r is minus 1 over lambda times 2.197. Recall that minus 1 over lambda was our time constant, cap t, so we see the rise time is 2.197 times the time constant. In other words, the rise time is about twice the time constant of the system. So no, the rise time and the time constant are not the same, although they are related